Hello everyone, welcome to the Luminous Science. In our previous video, we had seen about simple harmonic oscillation. And in this video, now we are going to discuss about the anharmonic oscillation. So let us see what does this anharmonic oscillator mean. Real molecules do not exactly obey the law of simple harmonic motion. Real bond, although elastic, are not so homogeneous as to obey the Hooke's law. If the bond between the atoms is stretched, for instance, there comes a point at which it will break the molecule and dissociate into atom. Thus, although for any small compression and extension, the bond may be taken as perfectly elastic. So what does this statement is saying? Always the molecules are bound together by two atoms. But in some situations and in some cases, if there is loss of energy or gain of energy, the bond between those atoms present in the same molecule may get compressed or they may get extended. So during the process of this compression and extension, the bond between the atoms in a molecule can break. So any bond which comes in action of compression or extension which is greater than their threshold energy will lead to breakage of the bond. So the bond which breaks between the atoms present in the same molecule are completely elastic in nature. And so now what is this term called as elastic? So what does this mean? So this means that when there is a break of energy taking place between the bonds of the two atoms, there will be no exchange of energy taking place, but the amount of energy which is required to break the bond will be equally divided between the atoms which have undergone the bond breakage. Now let us see, if for an anharmonic oscillator, Schrodinger wave equation for vibrational energies. So the Schrodinger wave equation for a vibrational energy for an anharmonic oscillator is given as EV is equal to V plus 1 by 2 into omega dash oscillation minus V plus 1 by 2 of omega dash oscillation into XE. This is also called as xi E. So here we can see V is nothing but the vibrational quantum number and XE is the anharmonicity constant. Now, if we put various value for V, that is V is equal to 0, 1, 2 respectively, then the energy value will be E naught is equal to 1 by 2 omega dash oscillation minus 1 by 4 omega dash oscillation into xi E. And similarly, for the value of V is equal to 1, also E1 will give us 3 by 2 omega dash oscillation minus 9 by 4 omega dash oscillation into XE. And similarly, for V2, we can see E2 which is equal to 5 by 2 omega dash oscillation minus 25 by 4 omega dash oscillation into xi E. So these are the expressions or the values which we get for the value of energy when we put different vibrational quantum numbers as 0, 1, 2 respectively. And as the quantum number of anharmonic diatomic molecule increases, the energy of the energy level decreases. Why does this energy level decreases? Like, as we know, the wavelength is inversely proportional to energy. Wavelength is inversely proportional to energy, and so does the increase in the quantum number, and we know these quantum numbers are associated with the wavelength, and so does when the quantum number increases, the energy of the energy level will decrease. What does this energy level mean? We know that there are different energy levels which will be associated to the molecule. So as the quantum number increases, the distance between them, that is delta E, which is nothing but the energy of the energy level, will automatically decrease. So the complete detailed explanation regarding this concept will be seen in further sessions. Now, let us see about the selection rule. So, why is this selection rule important? So, in the previous video, we have already seen that the transition of electrons from their lower energy to higher energy or from higher energy level to lower energy level are purely selected, because in some of the spectroscopic method and also some transitions needs a specific characteristic or a specific type of criteria that need to be fulfilled to get transisted or to get transformed. So now let us see the selection rule which is involved in the concept of anharmonic oscillator. So because of the anharmonicity, the vibrational transitions are not confined to the adjacent levels only, but they may occur in different levels, so that delta V which is nothing but vibrational quantum number, it can be plus or minus 1, plus or minus 2, or plus or minus 3, and so on. So what does this statement mean is, if we consider the energy level, that is different energy levels. So in the previous spectroscopic methods and transitions, we have seen that the electrons which are present, let us consider 1, 2, 3, 4. These are the 4 energy level. So in previous spectroscopic method, we have seen that electrons will transist only to their adjacent or corresponding energy level. That is, an electron which is present in energy level 1 will only jump or get transisted to energy level 2. And similarly, if any electron was present in energy level 2, then it would jump or get transferred to the energy level 3. And similarly, the backward movement or depromotion of electrons would also take place in the same way. For example, if electron was in 4th energy level, then it would come to energy level 3 and not directly to energy number 1. But here, in case of anharmonic oscillator, we can see the transition may take place in plus or minus 1, that is from the energy level 1 to energy level 2, and also plus or minus 2, that is from 1 to 3, which is plus 2, and also depromotion may also take place from energy level 3 to energy level 1, which is minus 2, and thus so on. So which means that transition may happen from 0 to 1, 0 to 2, 0 to 3, and so on. So in simple harmonic oscillator, that is in case of harmonic oscillator, we have seen that transition takes place only to the adjacent energy level, but here we can see they can also get transisted from 0 to 1, 2, 3, and so on. The energy level will continue, and the line appearing due to transition and the line which will appear, which is in the case of spectroscopy, we will see different types of lines or representations. So when we see the line which is due to the transition from V0 to V1, and this is known as the fundamental band. Fundamental band, which we can also call as the basic band. So this band can only be seen when V0. So the line which occurs due to the transition of electrons from V0 to V1, this is known as fundamental band. And the line appearing due to the transition from V0 to V2 is known as first overtone band. So the line which we see due to the transition of V0 to V1 is called as fundamental band, and the line which we see due to the transition from V0 to V2 is called as first overtone band. And similarly, the line which we can see due to the transition from V0 to V3 is called as second overtone band. And similarly, when the line appearance due to transition from V0 to V4, it is known as third overtone band. And so as the numbering or naming will be given depending upon the transition we see, that is fundamental band, first overtone band, second overtone band, third overtone band, and so on. Now let us see different cases and also the different energy values that we get for the fundamental band, first overtone band, and second overtone band. Now let us consider the first case, that is the transition which we see from V0 to V1. So for this case, the energy expression that we are going to write is E1 minus E0. So delta EV, which is given by 3 by 2 omega dash oscillation minus 9 by 4 omega dash oscillation into XE minus of 1 by 2 omega dash oscillation minus 1 by 4 omega dash oscillation into XE. So how did we get this expression? So in the above page, we had seen that by gaining the expression, that is when V is equal to 0, what will be the energy, and when V is equal to 1, what will be the energy, and thus knowing the expression from that, we have substituted the value of E1 and E0 from that equation which we have written, and when we rearrange them, we get the following expression, that is delta EV is equal to 3 by 2 omega dash oscillation minus 9 by 4 omega dash oscillation into XE minus 1 by 2 omega dash oscillation. Here minus into minus, it is plus, so we have written plus 1 by 4 omega dash oscillation into XE. Now we'll rearrange the equation so that denominator gets same, that is 3 by 2 omega dash oscillation minus 1 by 2 omega dash oscillation, which was here. We have rearranged corresponding to their denominators, and plus 1 by 4 omega dash oscillation into XE minus 9 by 4 omega dash SE. Now on calculating and evaluating the expressions and also taking away the common terms, that is here we can see omega dash oscillation is common. So delta EV is equal to omega dash oscillation into 3 by 2 minus 1 by 2 plus 1 by 4 minus 9 by 4 into omega dash oscillation into XE. And on further calculation and evaluation, we'll get 1 omega dash oscillation minus 1 into minus 8 by 4 into omega dash oscillation into XE. And on further evaluation, we'll get delta EV is equal to omega dash oscillation minus 2 omega dash oscillation into XE. And finally, we'll get the expression for fundamental band of delta EV, that is delta EV is equal to omega dash oscillation into 1 minus 2 XE. So this is the value of energy for the fundamental band which we have obtained when transition takes place from V0 to V1. So here we need to consider the expressions for energy, that is when V is equal to 0, what will be the expression for E, and when V is equal to 1, what is the expression for E we get. And on substituting them and on further evaluation, we'll get the final equation, that is delta EV is equal to omega dash oscillation into 1 minus 2 XE, which is the equation or the value of delta EV for a fundamental band. Now if we see the second case, That is when the transition takes place from V is equal to 0 to V is equal to 2. So delta E which is nothing but the difference in the energy level. So to get this, we'll write E2 minus E0. So similar to case 1 where we have substituted the value of E1 and E0, here also we'll consider the value of E2 and E1. So delta E which is equal to 5 by 2 omega dash oscillation minus 25 by 4 omega dash oscillation into Xe minus, here we have written minus, so here also minus 1 by 2 omega dash oscillation minus 1 by 4 omega dash oscillation into Xe. Now here it is minus into minus plus. So this is the only change we have made, and we get our next expression, that is delta E is equal to 5 by 2 omega dash oscillation minus 25 by 4 omega dash oscillation into Xe minus 1 by 2 omega dash oscillation plus 1 by 4 omega dash oscillation into Xe. Now the thing which we did in the case number 1, that is getting the denominators together and evaluating them, here also we have did the same thing. That is 5 by 2, here it is 1 by 2. So we have grouped them. This is called as grouping. So we'll get the next equation as 5 by 2 minus 1 by 2 into omega dash oscillation, because this is the common term which is included, and here we have got plus, so we'll write here also plus 1 by 4 minus, here it is minus 25 by 4, so here also minus 25 by 4, and the common terms which are included here are omega dash oscillation and Xe, omega dash oscillation and Xe. So this is what we have put here. And on further evaluation, we'll get delta E is equal to 2 omega dash oscillation minus 6 omega dash oscillation into Xe. On further evaluation and taking out the common, here we have taken the common thing out, that is 2 omega oscillation into 1 minus 3 Xe, so which gives the value of first overtone band. So here when we take 2 as common, the remaining part is 1. We have written 1, and 2 3s are 6. Since we have taken 2 as the common term, the remaining term will be 3, and therefore 3Xe. So the common terms which we have taken here is 2 omega dash oscillation, and thus here we can see the remaining part, that is 1 minus 3Xe. So this will be the value of the difference in energy delta E, which is the first overtone band expression. And similarly, now if we consider the case 3, that is for the transition which takes place from V is equal to 0 to V is equal to 3. On substituting and evaluating in the similar way that we have done in case 1 and 2, we'll get the value for delta E as 3 omega naught oscillation into 1 minus 4 Xe. So here in the final equation, we will be taking 3 omega dash oscillation as the common term, and the remaining term will be 1 minus 4 Xe. So this is the expression for energy for a second overtone band. And here we can see a note, the overtone band are less intense than the fundamental band and hot band. So what are this hot band? We'll see in the next concept. So here there is a point or a note to be taken, that is overtone band are less intense. Less intense, what is that? Less intense means the appearance or the brightness of the overtone band will be less when compared to the fundamental band and the hot band. So they will be a more brighter in color and they will appear to a sharp eye point. But whereas this overtone band will be less intense and will have a very dim color when compared to this fundamental and hot band. So the intensity order will be, so the intensity at what brightness or how sharp the bands will appear to us, and their order is omega dash F. F is nothing but the fundamental band, omega dash 1, omega dash 2. This is nothing but the first overtone band. This is the second overtone band. So the intensity will be omega dash fundamental will have a more intensity when compared to omega dash 1 when compared to omega dash 2. Now let us see what does this hot bands mean. The lowest vibrational energy level, that is V is equal to 0. So V is equal to 0 when we consider an energy level. The lowest energy level or the lowest vibrational energy level in any atom will be 0. Is occupied only at room temperature. So the energy level of 0 will only be occupied at the room temperature. So most of the vibrational energy transitions will originate from V is equal to 0 level. With increase in temperature, the molecules will vibrate from V is equal to 0 to V is equal to 1, and thus sufficient number of molecules will migrate and occupy the V is equal to 0 level at higher temperature. This permits vibrational transitions to originate from V is equal to 1 level. Such transitions from V1 level to the higher energy level produce a spectral line, which are known as the hot band. With rise in temperature, the intensity of hot bands also increases. So what does this statement actually mean is, usually in the room temperature, the electrons or the atoms will always lie at their least energy level, that is usually be 0. So as temperature increases, usually the transitions of electrons or atoms will take place from the energy level 0 to their higher energy level. That is, it might be to energy level 1, 2 or 3. So, but initially at room temperature, the transition will take place from 0. But in some cases, what happens, as the temperature increases, some of the electrons or atoms which are present in the energy level 0 might migrate into energy level 1. they might occupy the energy level 1. So as the electron decreases, or the movement of electrons will increase from V0 to V1. And so thus the transition which takes place from V1 to the next adjacent or corresponding or any other higher energy level, and such bands which are seen due to transition are called as hot bands. So in the previous sessions, or usually we know that the fundamental bands or any kind of transitions will take place from when V will be equal to 0. So the lowest energy level or the fundamental energy level will be 0. So any kind of transition that occur will usually take place with respect to V is equal to 0, or where the energy level will be equal to 0, and the transition which takes place from 0 to energy level 1, they are called as fundamental bands. And respectively, the transitions or the lines which we can see due to the transition of electron from energy level 0 to energy level 2 is called as first overtone band. But here in case of hot band, we can see that transition will initially occur from V is equal to 1 and not from V is equal to 0, and therefore delta V will be equal to plus or minus 1. So here also we can see the transition will only be with respect to the adjacent band. That is, the transition we can see is from V is equal to 1 to V is equal to 2, and therefore to calculate delta E, we will see E2 minus E1. Substituting the corresponding values of E2 and E1, we can see here 5 by 2 omega dash oscillation minus 25 by 4 omega dash oscillation into XE minus 3 by 2 minus 4 by 9 into omega dash oscillation into XE. On evaluating this equation, we'll get the next equation, that is delta E is equal to omega dash oscillation minus 4 into omega dash oscillation into Xc. So here the common term we can see is omega dash oscillation, and thus taking this common, we can see delta E is equal to omega dash oscillation into 1 minus 4 into Xe. So this is the equation which is related to delta E for any hot band. Now let us see the modes of molecular vibration. So what is this modes of molecular vibration and how can we calculate this? First, let us see a molecule consists of n number of atoms. So the number of atoms which is present in a molecule are represented in terms of S. Has total degree of freedom which is equal to 3n. So if a molecule consists of n number of atoms, then the total number of degree of freedom that particular molecule can contain is equal to 3n. Now let us see for a linear molecule. So when we consider a linear molecule, its rotational degree of freedom will be 2 and its translational degree of freedom will be 3, and therefore vibrational degree of freedom. So to calculate the vibrational degree of freedom, we have the equation as total degree of freedom minus rotational degree of freedom plus translational degree of freedom. So generally, to calculate the vibrational degree of freedom, we have this given equation, that is total degree of freedom minus rotational plus translational degree of freedom. And so thus to calculate this, so this is a general equation which we are seeing for any kind of linear molecule. So as we saw that any linear molecule will have a rotational degree of freedom which is equal to 2 and translational degree of freedom which is equal to C. 3. So when we have to calculate the total degree of freedom, like as mentioned before, the total degree of freedom a molecule can have is 3n. So substituting the corresponding value in this equation, that is the total degree of freedom is 3n. Here it is 3n, and here we have got minus into the rotational degree of freedom. Here it is rotational is 2 and the translational degree is 3. So 2 plus 3 will be 5, and therefore the equation to calculate the number of vibrational degree of freedom for a linear molecule will be 3n minus 5, where n will be the number of atom which is present in that particular molecule. So a linear molecule has 3n minus 5 fundamental vibration modes, and for a diatomic molecule, if n is equal to 2, mode of vibration will be, so substituting, now we will consider a diatomic molecule. So when it is a diatomic molecule, then obviously the value of n will be equal to 2. So substituting the value of 2 to this equation, that is 3n minus 5. In place of n, we'll put 2, that is 3 into 2 minus 5. So we'll get the answer is 1. So the number of vibrations or the number of mode of vibration that a molecule can possess is 1. So we'll see few more examples related to this. Before directly going into the examples, let's also see for non-linear molecule and for polyatomic molecules also. But before that, let us see a few important note that we have to see for a linear molecule. Thus, there can be only one mode of vibration for a diatomic linear molecule. In case of homonuclear diatomic molecule, because of there's zero dipole moment for all bond length, no vibrational energy exchange could be possible, and as a result, such molecules would be infrared inactive. So here, when it comes to homonuclear molecule, what is this homonuclear molecule? Homonuclear molecule is those type of molecule where there are same kind of atom present in a molecule, like for example H2, N2, O2. So since there are homonuclear, that is same type of atoms are present, and since there is same type of atoms present in the molecule, obviously their dipole moment will be zero. And since there is no dipole moment, and we have seen that for any kind of vibrational spectra or to possess a vibrational energy, we need a dipole moment when there is compression or extension of the bond. Since their dipole moment will be zero, obviously there would be no exchange of energy taking place. So if there is no exchange of energy taking place, which means that the given molecule is infrared inactive. Why is this term infrared inactive came? Means they cannot possess any kind of transition when they are under the study of microscopy if their dipole moment is zero. So this is seen only in the case of homonuclear diatomic molecule. But apart from that, in any heteronuclear diatomic molecule, heteronuclear is nothing but atom molecules which have different kinds of atoms in it, like HCl, NO, CO, etc. The vibration in dipole moment is due to the fluctuation in the bond length, would make this molecule infrared active. So since we know in case of homonuclear diatomic molecules, their bond length will be same. Since their bond length is same, their dipole moment will be zero. Whereas in case of heteronuclear diatomic molecule, obviously their size will be different. And also the nucleus which is present in these atoms are completely different from one another. Since the nucleus which is present is also different, obviously their dipole moment will also be different due to the fluctuations which is seen in the bond length. And so thus, due to difference in their bond length, there will be difference in the dipole moment, which will actually make them infrared active. Now let us see what is the fundamental equation for a non-linear molecule. So when it comes to a non-linear molecule, the rotational degree of freedom will be 3 and translational degree of freedom will be also 3, and therefore the formula which we have seen for the vibrational degree of freedom, which is nothing but total number of degree of freedom minus rotational plus translational degree of freedom. Substituting the respected values in that equation, that is we know the total number of degree that a molecule can possess is 3n, minus here it is 3 for both rotational degree and also translational degree of freedom, and therefore 3 plus 3, which will give us 3n minus 6. So we have got the vibrational degree of freedom for a linear molecule as 3n minus 5, and for a non-linear molecule, the vibrational degree of freedom is 3n minus 6. And so a non-linear molecule will have 3n minus 6 vibrational degree of freedom. So here we know n stands for the number of atoms which is present in a molecule. And for any kind of polyatomic molecule, there are some polyatomic molecule which do not possess a permanent dipole, but because of certain moles of vibrations develop of fluctuations dipole and respond to the infrared region of the electromagnetic rotations. So usually some of the polyatomic molecule will not possess a permanent dipole moment. So this is because there will be presence of 3 or more atoms in a single molecule. So their bond length might be different or same. If there are same kind of atom present in a molecule also, there will be obviously no dipole moment, that is zero dipole moment. If there are zero dipole moment, obviously we know they are infrared inactive. But in some cases, in some examples of molecules, we can see there will be fluctuation in the bond length, which will actually lead to dipole in some of the cases, but not in all the cases as we have considered till now. So due to fluctuation of dipole moment, and they might respond to infrared region. The presence of dipole moment in some cases will lead to a respond in infrared region, making them infrared active. And from that we can get a IR spectra. Now let us consider some of the examples of linear and bent triatomic molecule. So now let us consider a linear triatomic molecule. So now let us consider a linear triatomic molecule, that is carbon dioxide, CO2. So in CO2 it contains 3 atoms, that is 1 carbon and 2 oxygen, which is 3. Therefore N is equal to 3. And we know that carbon dioxide is a linear molecule. So the number of vibrational mode for a linear molecule will be 3n minus 5. So here n represents the number of atoms. So substituting that 3 into 3 minus 5, we will get 4. So the number of allowed modes of vibrations in a molecule of carbon dioxide is 4. So now let us see what are those 4 modes of vibration. The first mode of vibration is this one. So this is the structure of carbon dioxide. The first mode is that since both the oxygen are more electronegative when compared to the carbon which is present at the center, the pull will be obviously towards the oxygen rather than the carbon. And in second case, we can see the bond length between the carbon and one of the oxygen will be strong when compared to the carbon and other oxygen. So this will actually increase the pull between these region, and thus this will be compressed and this will be elongated. And in the same way, the oxygen which is present at the either side of the carbon might move in the opposite direction of the carbon atom, creating a dipole moment. So here we can see the oxygen is running downward. The picture 3 and 4 are similar, but here we can see the oxygen are running upward, whereas the carbon is running downward. Here the oxygen is running downward, whereas carbon is running upward. As we had seen the four modes of vibration, thus we see that the fourth mode of vibration is identical with the third one, that is the downward and upward movement, and also vice versa of carbon and oxygen molecule. The frequencies associated with the fourth and the third one is the same. So the frequency which is associated with the third mode and the fourth mode of vibrations are same. Such motions which are identical in all aspects except the directions are called as degeneration. So, in case of carbon dioxide, third mode is doubly degenerated. That is, the fourth mode is another bonding type which is identical in character and frequency to the third. So, here we can also see another term called as degeneration. So, what is this degeneration? Usually, the meaning of degeneration starts to another form of a molecule, but its representation is quite different. So, here we can see in figure or the mode of vibration of 3 and 4. So here this is 3 and this is 4. We can see here that the mode of vibration is same. Here both the oxygen atom are moving in one direction while the carbon is moving in another direction. Here also fourth one, the two oxygen atoms are moving in one direction while the carbon atom present is moving in opposite direction. Both the type of vibrations are same, but the direction they are ongoing is different. So such kind of mode of vibrations are termed to as degeneration, and so thus the third mode is called as doubly degenerated, since there are two types of or two similar mode of vibrations which can be seen. Since 3 and 4 are same, their bonding type is also same. They are linear and the position of carbon and oxygen are also same, and so thus their character and frequencies are also same. Now let us see for a bent triatomic molecule, that is water. We know the structure of water, it is a bent structure. In water also we can see there are 3 atoms, and so N is equal to 3. Bent is nothing but they are non-linear molecule, and since it is a non-linear molecule, hence the number of mode of vibration is given by the equation 3n minus 6. Substituting the value of n, that is 3 into 3 minus 6 will give us 3, that is 9 minus 6 will give us 3, and therefore the allowed mode of vibrations are 3, and they are. So there are 3 modes of vibration which is seen in water molecule. So these are the vibrations. Here we can see both the hydrogen atoms are moving in opposite direction to oxygen, and since they are moving in opposite direction, that is in opposite direction, obviously when they move, the oxygen which is present will tend to move upward, so that it maintains a symmetric structure, and also the bond, hydrogen bond, would not break. And in second mode of vibration, we can see both the hydrogen atoms are moving sideways, and here also we can see the first mode of vibration and second mode of vibration are almost similar, but their direction, movement of direction is different. And in third mode of vibration, we can see one of the hydrogen atom is being extended while the oxygen and the other hydrogen atom which is present in the bond are moving in their opposite direction. So there is an equal and opposite force which is acting between the oxygen and hydrogen, making them held together and be balanced. And here all the 3 modes of vibrations are IR active. Why IR active? Since each of them is accompanied by change of dipole moment. Since there is presence of dipole moment in all the 3 cases, all the 3 modes of vibrations are IR active. It is easy to bend a molecule than to stretch it. Hence, bending frequency is generally lower than the stretching frequency. Also, it is easy to stretch a molecule symmetrically than to stretch it asymmetrically. So, here is one more point we need to keep in mind, that stretching a molecule symmetrically is more easier when compared to asymmetric stretching. And also, bending frequency is generally lower than the stretching frequency. So, any molecule can be bent easily rather than stretching. The bending frequency. So we know that the frequency is directly proportional to the energy associated with the molecule. If bending is easier, then obviously the amount of energy required to bend a molecule or the bond between the atom present in the molecule will also be less. While in case of stretching, we need more energy to stretch the bond, and so thus the stretching frequency will also be more. Now let us see applications of IR spectroscopy, which is also called as vibrational spectroscopy. First one is qualitative analysis can be easily done by comparing the spectrum of unknown sample with the standard one. What is this qualitative? Qualitative is nothing but what is present, not how much is present, but what is present, what element or which molecule is present can be easily easily determined by just comparing the spectral values with the unknown sample, that is with the standard one. Comparing the unknown sample with the standard one will actually give us the qualitative analysis. And it is also used to determine the purity of compound, which is also related to qualitative analysis. By knowing the standard value, we can actually check how much pure the compound is. And it is used to estimate the water in the sample also. It is also used to estimate the sample. The presence of sample or absence of sample in a particular element or in particular compound will give us different readings. So comparing all of them with the standard one, we can actually estimate the water which is present in the sample. For diatomic molecule, the force constant, bond energy and bond length can also be calculated. By knowing the spectral lines or any other data which can be obtained from the IR or vibrational spectroscopy, we can actually determine the following, that is the force constant, bond energy and bond length. The next one is each type of bond and functional groups give a characteristic peak, and it is possible to identify the type of bond and the functional group, since each element, each functional group and each atom present in the periodic table will have their own characteristic peak and also characteristic feature. By knowing these standard values, one can actually easily find out or determine the type of functional group or what type of bond, that is covalent bond, ionic bond, coordination bond, metallic bond, can also be known by the IR spectra. The progress of most organic reactions can be monitored readily by examining the IR spectra of the aliquils withdrawn. So during any course of organic reactions, the type of bond form or the type of functional groups which are added to it, by knowing them, we can actually examine, which usually help us in examining through IR spectra. And also by absorbing the absorption band at different regions, the presence of functional group and structures of unknown compound can also be identified, not only by the spectral peaks that we get, but also we know that in spectroscopy there are different types of absorption bands which can be seen, like for example UV, visible, X-ray, gamma ray, then infrared region. So depending on what type of electromagnetic radiation a particular molecule or an atom is absorbing, we can also determine the type of molecule which is present and also the type of functional group, and also in some cases we can exactly determine the structure of the compound. So these were some of the applications which are related to IR spectroscopy. In our part 1 video, we had seen about the vibrational spectroscopy and about a few derivations related to simple harmonic oscillator. In this video, we had covered definitions of hot band, fundamental band, first overtone, second overtone, and also derivations and equations related to anharmonic oscillations, and also the number of rotational, vibration and vibrational modes for linear and non-linear molecules. And also finally we saw the applications of IR spectroscopy. Hope this video was helpful to you guys. See you all in my next video. If you have liked this video, kindly like, share and subscribe. See you all.